So as we have been discussing last time, if you decide to go with a set of input messages as one block, and then you arbitrarily map that into a set of output messages as one block as well, the number of possibilities is very large, and accordingly, the size of the key that you have to share is very large as well. Okay. Remember last time we said, for example, for the case of n bits, for the case of n bits, the size of the key is going to be 2 to the power n and then factorial, right? Okay. And sharing that key is going to be really a cumbersome operation. It's going to be a very big amount of bits or big amount of data to share just for key sharing between the transmitter and the receiver, or the ciphering, deciphering side, or encryption, decryption side. Okay. It's just an example of the fact that the mapping can be arbitrarily. So it shows you here, for example, one possibility of mapping from this plain text to this ciphertext, and there's another possibility here from this plain text to this ciphertext. Okay. So if this is the case, if doing it this way is nice because it's secure, but on the other side, it's not nice because of the practicality that sharing the key is going to be a big problem, what is the alternative? And the alternative for that came from a cryptography scientist called Fiestel, and he proposed to use cipher that alternates between the two operations that we mentioned earlier. Remember, we said you can do encryption with one of two ways. Of course, you can mix them, okay? And one of you asked that question last time. She was sitting here, okay? Sorry? Nora. Nora, yeah, okay. She was sitting here. Nora was sitting here, okay? So, yes, you can mix, and this guy decided, okay, how about we do this operation? So we start actually with a small key, limited amount or limited size of the key. But then the way we do the encryption is going to make things complicated such that it's going to be equivalent to the situation that we showed earlier without the need to actually have that amount of large key, just for the fact that, again, why did we choose to do that 4 to 4 bit mapping or n to n? Because we wanted to be as much as possible immune to crypt analysis, right? So we don't want to keep anything in the cipher that preserves the statistics of the original plain text, right? So that was the best way to do it. Now, but it had a practicality issue. Now what Fiestel said is that we can achieve the same thing, which is basically making sure that the ciphertext is almost independent from the statistics of the plain text, but without having to use that amount of key size, okay? By doing what? By doing substitution and permutation. Did he come up with this idea just out of the blue? So he was sitting over there and then he said, okay, how about we try substitution and then permutation? It happens in some cases, but in this case, no, he had actually some intuitions. The intuitions came from, and it's coming in a couple of slides, the intuition came from, remember the guy called Shannon, whom we studied his theories about how to measure security and how to achieve perfect secrecy by using the one-time pad and so on. One of the things that Shannon mentioned is that if you really want to be immune, and he has a mathematical proof for that, if you want to be immune against crypt analysis, you have to achieve two properties in the ciphertext, right? Such that it will no longer preserve the statistics of the plain text. The two properties are confusion and diffusion, okay? So what does these two properties mean? We will come to them in a couple of slides. But just to summarize them very quickly, you want to make sure that the output, every single character or every single word in the output cipher does not rely on a statistics of a single input word. It relies on a collection of statistics of input words, okay? This is the property called diffusion. And then the confusion property is the fact that it's going to be very difficult to to figure out the encryption, decryption as an input-output relation, whether it's linear. The worst case scenario is that it becomes linear, or even non-linear. It's very complicated, such that you cannot go ahead and plot a function that shows you how to map the input to the output. Okay? If you can prevent those two things, so basically achieve those two properties, one of them is the diffusion and the other one is confusion, then your cipher is no longer related statistically to the input statistics of the language, which means that cryptanalysis is not going to work on your system. It's going to be as complicated as brute force trials. Okay? So, driven by intuitions from those two properties, Fiestel came up with the idea, okay, let's do substitution and permutation. And the target of those two operations actually, so the way he does the substitution is making sure that you achieve diffusion, and the way he performs the permutation is mainly to make sure that you achieve also confusion. Okay? So this one, confusion, means it guarantees that you don't have a clear input-output relation between the cipher and the decipher, a relation that someone can find by just having a few plain text, ciphertext pairs, right? That one will not be able to use those to some kind of interpolate a relation between the input and the output in the ciphering operation, okay? That's for the permutation, and that relates to confusion. Diffusion is going to happen by substitution, the substitution methods that he's going to use, including how he uses the key, how he generates subkeys from that key, how he mixes the key with the ciphertext, the plain text, to produce the ciphertext, which is the function of encryption. All of these guarantees that you end up with any single output in the cipher relies on many of the input plain texts, not just one of them, okay? And that means what? If you rely, let's say if you reach the optimum case, every single alphabet in the output relies on all the possible alphabets of the input. So this means what? All the output ciphertext will have the same statistics. They will all have equal probability to occur, right? Because each one of them is just simply the sum of occurrences of all the other input characters, right? So if you try to plot the statistics of the occurrences of the output cipher for every letter, you will find that every letter has equal probability, which means you can no longer arrange them to say this is the highest occurring and this is the lowest and this is the lowest, and accordingly you cannot map them back to what is the highest in the plain text, what's the next, and so on, right? Remember that graph that I showed you a couple of lectures ago that shows how the statistics are in the plain text case, and then in all those ciphers that we were doing, it was still preserving that higher probability, lower probability. And the ideal case is this: when you have all the output ciphertext, right, occurring with the same probability. They all occur with the same probability. So which one is the highest occurring? I don't know. There's no way to figure it out. And my only way to solve it now is trying all the different combinations. That's a brute force, right? Okay? Okay, so let's see how this guy uses those two operations to produce a ciphertext from a shorter small key as well as the plain text. This slide is talking about the diffusion and confusion. So before going to the Fiestel operation, okay, again, what are these two operations? I already described them, but I'm going to repeat them here through the slide. So the statistical structure of the plain text is dissipated into the ciphertext. So as I mentioned, this is achieved by making sure that every output letter in the ciphertext relies on many of the input plain text letters, okay? So eventually, each one of the output cipher is going to have equal statistics approximately to all the others, okay? And this shows you that plain text digit affect the value of many ciphertext digit, okay? The second thing, the confusion, seeks to make the relationship between the statistics of the ciphertext and the value of the encryption key as complex as possible. So that's the key. The relationship between the statistics and the key is a complex relation. So you cannot, just by having a few plain text ciphertext pairs, just somehow interpolate a relation. Because if you can do that, you will be able to break the key again, okay? But again, even if the attacker can get handle on the statistics of the ciphertext. The way in which the key was used to produce that ciphertext is going to be so complex such that you cannot figure out that relation. You cannot figure out how it happened. Okay? And accordingly, you cannot reverse the encryption operation. Back to the Fiestel, how it's done. So this is how it's done. Two things, okay? First of all, it's done in rounds. So you do an encryption or an operation, and then you keep repeating that operation several times, okay? In each one of those rounds, you do the two important operations that we mentioned. One of them is substitution, the other one is permutation, okay? Where do we see that? So this is a single round that you see here, okay? Moving from the first block to the second block. What's happening in that case? By the way, the left side shows you the encryption process or the ciphering. The right side shows you the decryption, the inverse operation, when you want to recover back the plain text. So you get the plain text, you divide the block of plain text into two halves. We call them the left and the right, or you can call them the left side is typically upper digits and the right side is lower digits. So either you call them upper and lower or left and right, okay? As you see them here in the first part, okay? And then you do the following. You take the right side or the lower side, you perform encryption with a subkey to that. I will talk later on about what's the subkey. Okay? But anyways, this is an operation that includes a key, an encryption function, a plain text, right? Correct? So we have a plain text, which is this part of the plain text. We have a key, we have an encryption function that mixes the key with the plain text, right? So this is a substitution operation, right? But further to this substitution, which says that whatever output here is going to rely on the key and only this part of the bits, to increase the idea of diffusion, you also mix those with the upper side or the left side by using an XOR here. So now the output that you will get here is going to be something that relies on every single bit of the input as well as the key, right? So this ensures that you reach maximum possible diffusion, right? And this is happening by what we did here is a substitution operation. Clear? Anyone is confused about what's happening between this, and the key? The key part? Okay, how did we represent encryption, generally speaking? Typically, we represented the encryption function by using what? A small block diagram that says, here is your plain text, right? Here is a key. Here is some encryption function that mixes those and produces ciphertext, right? This is how we said encryption in general happens. We mentioned that very early when we talked about encryption, right? We said it's some function. Typically, that function is known because it's a standard. The only private part is the key, right? And I have my plain text. I mix the plain text using that standardized function, which is well known to everyone, with the key that produces a ciphertext, right? That's exactly what's happening in this part. So I have the plain text, I have the key, and they are mixed together with an encryption function, F, right? This is going to produce something here which is encrypted, cipher, right? But the problem with this is it does not have full diffusion because the output bits here does not rely on all the words of the input block, but relies only on half of it. So to make sure that whatever we get as an output final cipher from that round relies on every single input bit, right? We also mix whatever we encrypt here using the right part with the key. We mix that with the left part as well using an XOR. So the result that we get here is going to rely on this, and the key, right? Okay? So now we guarantee that we produce here the right part on level 1, so after the end of round 1, right? Which is a substitution operation that combines everything from the input with a key in a particular way, okay? The idea of doing the mix here with only half of it, because this allows you to use a smaller key size. Okay, so the idea here is now you can use a key which is only as large as half of your data block instead of using a key which is equal to the data block in size. Okay, that's why he does this 2 steps encryption using substitution. Okay. Okay, and we mentioned that in every round you also have to do some kind of permutation. So here is how the permutation is achieved. You finish this to produce this part, right? Combining those two together with the key to produce this, and then you take this as it is, you put it as the left side. So now we did some permutation. With multiple rounds, the mix of substitution and permutation makes sure that things are really scrambled a lot. Okay?
But concept here, the left side is not encrypted yet, right? The left side is not encrypted because we have.
The left side is no longer there in the first place.
No. I mean in the substitution operation.
Okay.
The left side is not.
But it is mixed. When you XOR things together, they get mixed together. So it's mixed with the key eventually, right? It's as if you took the 2 sides, you XORed them, and then you XORed them with the key, right? So that's an encryption. Because the key is independent from both of them, and it's XORed with both of them, right? Eventually, it's somewhere in this XOR because the key is used here, right? Okay, so you cannot say it's not encrypted. It's not processed using a separate key, but with mixing it using when you XOR 2 things, you cannot recover the original one, right? Unless you know both of them, or unless you know one of them. Okay, otherwise you cannot recover the other one. Okay. So, yes. Yeah, it can be bits, it can be words, it can be letters, it can be anything. The operation is general. You will use the code for each letter. So eventually bits. Okay. Or you define an XOR operation equivalent at a non-binary domain. So in a domain of mod 26, you can define an XOR operation similar to the bit XOR operation. Okay? But generally speaking, yeah, here it's kind of assuming it's bits, just to move on here. Okay?
After round 1, the right side would be the left side.
Yes.
But if for example, if left side is known by any attacker or something.
Known where? We did not produce anything. This is only 1 round. This is no output yet. This is internal to the system, right? So now after this, you end up with left side, which has not been touched. It's just the right side, but moved to a different location, and a right side, which is a combination of everything, right? Next step, you will do that untouched part is going to be the one that gets mixed, right? And then whatever you put here is going to be something that comes out of a mix. So no longer plain things will not appear after only 2 rounds, right? But still, if you rely only on 2 rounds, this is not going to be sufficient. For the cases of the DES, you need at least 16 rounds. And the fact is, you should stop at 16. Why shouldn't I go beyond 16? I will tell you later on why. Okay? So remind me to tell you later on why. So if you do less than 16 in the DES, what you achieve is gonna be weak. And if you do more than 16, what you'll achieve is gonna be strong, but you have lost efficiency. You have done extra steps without any gain. Okay, this is the main reason. Why this is the case, I will talk about that later. How do you measure that this is the point that you have to stop? I will talk about that later. Okay? Any questions? So the Fiestel is repetitions of what we call here a single round. What's entailed in a single round? You have a block of text, you have a block of bits, let's talk about bits, okay, or block of alphabet, okay. And then you divide that into 2 halves, the upper half, the lower half, or the right half and the left half. Then for the right half, you mix that with the key, we call this the subkey, okay. And then you mix it using the encryption function, some defined encryption function, and then after that you XOR it with the left half to produce the output of that round, right side, okay? What about the left side of the output of the round? Is gonna be simply the right side moved up. So that's a permutation operation, okay? So the right side here at the output is always produced by substitution. The left side is always produced by permutation, okay? Yes.
كل مرة بتغير؟
sub key. This is not the key. It's called the sub key. Okay, so
from the
it's generated from the key. So in order to go through this operation, you need an actual key. You have a key with certain length, right? And then you do some function to generate from that key a group of sub keys. Each one is generated for each round. So there is a new sub key generated from the original key for each round. Okay? If you do 5 rounds, you need to generate 5 sub keys. If you do 10 rounds, 10 sub keys. Here, we're talking about 16 rounds. You need 16 sub keys derived from the original key. How do you derive them? What are the properties to make sure that you derive them correctly such that they do not destroy the security of your system? We will see that in a few slides. Okay, we will not see that in the context of Fiestel. We'll see that in the context of DES, which uses the Fiestel.
isn't the way it isn't يعني waste of size or something because we are doing 16 step to cipher. and
No,
cipher.
it requires, it's not a waste of size, it's a waste of, you mean you are consuming more computational or complexity. But the saving in this case is that the size of the key that you have to share is very small. Because we went only to this, such that you can achieve something from an encryption point of view, does achieve protection against cryptanalysis similar to the arbitrarily mapping of n words at the input to n words at the output, or n alphabets to n alphabets, right? What was the gain in that case? The only gain was to make sure that it's immune against cryptanalysis, right? When you do this with enough number of rounds, you achieve that because the statistics of the output is no longer reliant on the statistics of the input, right? And this means you are immune against cryptanalysis, but you have to share here a shorter key. You don't need to use a very large key. This is just a slide that shows you what are the main parameters that you can play with to change the strength or in general the security property of the Fiestel operation versus what will you lose if you do that. Like any parameter that you change, you make it larger or you make it smaller. And let's say, for example, if you make it larger, it will give you gain in terms of security. There is something else that you have to pay. So you lose something versus that, right? So you have to always balance all these parameters such that you achieve the performance that you want without losing too much on other performance measures, okay? So first, block size. When you increase the block size, this makes your encryption much stronger. It becomes much harder because, as we mentioned, when you increase the block size, a lot of the output relies on a lot of the input, which means cryptanalysis becomes even harder and harder and harder, right? Okay, so that's a gain. When you increase the block size, how much you encrypt each time, this will make your encryption stronger, but it comes at a cost. What's the cost? You need more memory, you need more computation time, because every computation relies on the size of the elements that you are trying to add, subtract, divide, multiply, okay? When you make the numbers larger, the computation takes more energy, takes more time, okay? So you have to balance that. Like pick the size that gives you enough strength in terms of the protection from a security point of view, but not too large to become prohibitive computationally and energy consumption wise, okay? Similarly, the key size. A larger key makes your encryption better. Why? A larger key protects against what? Against which attack? Brute force attack. So typically an attacker is trying to figure out the key. And what he or she is trying to do is just try every single possibility of the key value until they figure out the one that gives some reasonable outcome from the ciphertext. Then they say this is the key, right? When you make the key size larger, it means the attacker has to search through a much larger domain, which means that the attack takes longer time, more resources, and so on. It becomes harder to do, right? So the key size, when you increase the key size, it makes your system stronger, definitely, in terms of security. But again, a larger key size means you are dealing with larger numbers. Not only that, a larger key size means you have to share something much larger through the key sharing channel, whatever that is, which typically slows down your system. Because that channel is supposed to be somehow protected and secure, and the rate through that channel is going to be very low. So your system is going to slow down because you need to share a larger key. So you have to wait until the key arrives, and then you can transmit. Okay?
But even if the key is too is small, the root.
We are saying you are always gaining in one side, losing on the other side. If you make the key larger, you gain from protection, but you lose from speed of transmission, right? So you have to pick something in between that gives you reasonable speed of transmission, enough protection. In every one of those, there is a gain, a loss, right? So you have to balance somehow. It's a trade-off, okay? Number of rounds. When you increase the number of rounds, your system becomes more protected because that adds more confusion and diffusion, which means that it becomes harder to break using cryptanalysis, right? But on the other side, more rounds, what you mentioned, means that you'll take longer time to do the computation, and this means more energy consumption and slower rate eventually, because you need to finish one before sending the other, right? Okay. Sub-key generation algorithm. I mentioned that the sub-keys are generated from the original key, right? And that sub-key generation algorithm has to be such that it allows for almost a separation between the sub-keys, one and the other, so they don't look similar. That's number one. And number two, that using one of the sub-keys, you cannot easily discover what was the original key. So if you have, for some reason or the other, you have had access to one of those sub-keys, or you could solve the sub-key that was used in a particular stage, right? And you figured it out, it's very difficult from that sub-key to figure out what was the original key. So it has to be somehow derived from the original key through a very complicated computational process, such that recovering it back is very difficult. Taking it the other way is very difficult, okay? And by the way, this doesn't mean that the operation of derivation itself is difficult. No, there are, like the hashing operation, for example, there are operations that are irreversible. I know how it happens, but there is no inverse to that operation. I cannot take it back by applying it or reversing that operation to get something back from the input, right? So in that case, even if I know how it was derived and I know its value, I cannot just simply perform a reverse operation to get the original key, okay? So these are the two things that you want in the sub-key generation algorithm, that it has to be complicated enough such that you cannot recover the original key, and it has to make sure that the sub-keys are different enough from each other. We'll see later on why. Okay? Round function f, main objective of that, this is the function that performs the mixture between the key and the plain text. So that's the encryption function. That function has to be complex as much as possible, okay? So that you cannot somehow interpolate it. Remember when I told you that an attacker is always trying to interpolate the relation between the output ciphertext and the input, and if they can figure some plot of a function that allows that mapping, then I can give that function the ciphertext, it will produce the plain text. I've broken down the whole encryption, right? So if you use for example, if you use a linear function f that mixes the key with the cipher, then someone with a few plain text ciphertext is gonna put them on a graph, right? And then interpolate, and the relation that he or she is gonna get is gonna be a very good approximation of how the encryption happened, and then I can use that same graph to put the ciphertext, look for the graph, get the plain text, right? Okay, so it has to be somehow very complex such that I cannot really figure it out. And the worst case that I can do is that I use something linear. That's like very easy to interpolate, very easy to figure it out, okay? It has to be very highly nonlinear, okay? You have to keep in mind while designing the Fiestel is that most of the time the encryption and decryption operation is implemented in software. This is a practical aspect, not really like a key parameter thing. Why it's implemented in software most of the time? Because there are always upgrades to this process. So you can change the function, you can change the number of rounds, and things that are implemented in hardware are not flexible enough to be changed after they are implemented for the first time. They are kind of hardwired, while things that are implemented in a software can always change with a system software upgrade, right? So you send an upgrade, the system now performs a slightly different or a modified or an enhanced operation and so on. What is the problem when things are implemented in software, software generally speaking is slower than hardware. So you have to be, execution on software takes longer time because it runs on hardware, right? It's some logical operations that runs on a hardware. If the same logical operation is implemented by hardwiring it, there is no for loop or going through an if else, or it's just a signal that goes through and produces an output, right? So always software implementation of algorithms is slower when it's on a software, but the gain is that it's more flexible, okay? So the fact that this is gonna be implemented in software has to be kept in the designer's mind when they are designing the algorithm itself and the different parameters used. We want that to be executing within a very reasonable time, assuming a software platform. If you assume a hardware platform, then your assumption is not correct with reality, okay? Last but not least, this is kind of conflicting with this. So I want my methodology to be analyzable by the designer. Why? Because I want to figure out whether it will work really or not when I design it, right? Let me give you an example to kind of give like a funny idea about this. It's silly, but a funny idea, okay? Imagine that I want to produce a number at the output of a set of operations which is totally independent from the input. And then I try to make things very complicated. So I take an input, x, and then I take that through raising it to the power y, and then I take that through an integration, and then I take that through some square root operation, and then I take it through squaring operation, and then a differentiation operation, d by dx, and then a len operation, right? Such that I complicated things and I lost track what exactly is happening. But if you notice what's gonna happen, the output here is gonna always be equal to x, because I raised it to power, took the len, integrated and then differentiated, squared and then took the square root. So I did lots of things, very complicated, but because the system was too big for me, I mean not only 9 blocks, but imagine that this was 1,000 block of operations. And I lost track exactly what's happening to my signal. It might be that the output is that much, here it's the same, just to give a very trivial example, but it might be that the output is still highly related to the input and can be attacked with a very simple attack just because I was not able to figure out from the complexity that I tried to implement in the system, right? I over-designed and I did lots of things and then I lost track. Is this system really doing, like by initial intuition, is this system really doing strong encryption or not? I lost track, I cannot analyze it. I cannot figure out whether there is enough separation and there is no clear, easy relation between the input and the output. And trying to figure out this by trying it in the field takes a long time, right? It cannot be performed in the lab because I need to try infinite number of scenarios and see that in all these scenarios, it is strong, right? Might not be the case, so I have to keep it in the field for a long time. At that time, it might have been attacked hundreds of millions of times and people have been losing money and losing information and so on. So you still, even though you try to make the relation between the cipher and the plain text as complex as possible, right? But you have to keep it controlled. You have to keep this complexity controlled such that you as a designer can have a clear intuition whether your system is gonna work or not. Whether really it's gonna produce something at the output which is, as far as I can see it analytically, independent from the input, okay? So these are two conflicting. I want the function f here to be as complex as possible, but I have to keep that complexity controlled such that I can still analyze my system. Okay? Clear this part? Okay.
number of blocks ممكن يوصل لعدد فيديو 1000 مثلا blocks.
Number of which blocks?
زي 9 blocks حضرتك حطيتهم هو
I'm just talking about هنا مش blocks. هنا these are like kind of mathematical operations that you are trying to do. It can be anything, you don't know, right? The idea here is not really, because when you are designing those, and we'll see that in the DES, for example, you typically provide either equations for certain operations, and then you keep repeating that equation, for example, 16 times, right? That's what we do here in those rounds. Or you provide mapping that shows you for all possible inputs, for inputs here are zeros or ones, right? And where are they? In location 1 or 2 or 3 and 4. This is what defines the input. And for that particular situation, the output should look like this. So you provide some input-output mapping tables, right? Now, if you try to make the input-output mapping tables like scrambled around, you will not be able to notice after what will happen after 16 rounds. Is it going to recover the original or not, right? If you cannot really see a way to analyze it. So the example I gave was kind of a little bit outside, but just to make it simpler to understand what I mean by overcomplicating, such that you cannot analyze and you perform a very trivial mistake that makes your system weak because you're not able to realize what does it do. Okay. This slide is just showing you what is going to be the output at every single step and how it relates to the input. So doesn't add any information. It just shows you that in written statements. So it says that, remember, this is the lower or the right side, and this is the higher or the left side. So in any round, you take this number, you mix it with the key using the encryption function F, and then after that, you XOR it with the other one. And that's gonna be the output here. The mixture XORed with the left side. The output on the other side is gonna be simply the input as is. So this is just showing you what I tried to describe in operations and blocks with numbers, so you can see what changes and what stays as is and how they are related to each other. Okay, nothing new in this slide. Okay, same thing for the inverse operation when you are going through the decryption, but reversed. So the encryption flow follows on the Feistel block up to down, and the decryption follows down to up. So the operation, for example, in round 1, okay, if you use 16 rounds, round 1 is going to be using sub key 1, K1, right? And it's going to perform the operations, goes to round 2, 3, 4, 5 until we reach 16. When I recover, I'm going to use round 16 block in the inverse way, so the inverse of round 16 with the key number 16, and then go back to round 15, round 14, round 13, and so on until I reach round 1. Okay, so the decryption happens in an inverse order. Okay. Okay, let's take a break. طيب. So far we haven't really went into the DES, which is a standard used for encryption, for symmetric block cipher encryption, and that standard was produced by the NIST, the National Bureau of Standards and Technology, if I remember correctly. And they produced a standard called the Federal Information Processing Standard number 46. That was in 1977. So that's really a while ago, 1977, right? I was what, like 6, 7 years at that? Yeah, 5 years at that time. Okay. By the way, this standard until today is valid with some modifications as a strong encryption methodology. So it is still used until today with some modifications. We'll come to that later on, that addresses some of the weaknesses here. These weaknesses became an issue when computational power was increased. And you will see immediately that, for example, the standard defines that the key size is going to be 64-bit. And in fact, 8 bits of those are used for parity, so they are not independent bits. And the actual key size is only 56. عارفين الباريتي bits بتعمل ازاي مش كده يعني typically when you have a set of bits and you want to add a parity to them, you calculate the value of that bit based on the values of the protected ones. عدت عليكم الباريتي في اللوجيك صح؟
لا يعني ممكن يكون باسم تاني.
لا parity bits عدت عليكم. Even parity or odd parity, when you have a few bits and you want to add a bit to make the number of ones even ولا the number of ones يا نهار أبيض. في الديجيتال اهو اعترفت اهي ورطتكم. So anyways, generally طب انتوا مش خدتوا channel coding في الكوميونيكيشن؟ What's done in channel coding? What do you do?
في لخبطة في الحاجات وبعدين بيترتبوا.
Okay. لخبطها وبعدين بترتبها. Typically in channel coding you calculate values of some extra bits based on the values of your message. And then you append that to your transmitted signal. What does the receiver do? It receives the set of information and the set of check bits or error control bits, and then it compares, do they fit the relation that was supposed to be between them? If not, it means something has changed across the channel. So this means an error has happened, right? That's the generalized philosophy of error protection. Within computer, and particularly the memory access, errors can happen because of the voltages of transistors and overshoots and undershoots and stuff like that on the circuits of the computer. So in order to protect against those errors that might happen when you are writing or reading from the memory, they typically add for every 8 bits of information an extra one called the parity bit. And there are 2 ways to calculate that parity bit. Remember, it has to be a value dependent on the information, which is the other 8 bits, right? One way is called even parity. They are equal to each other. They perform the same. It's just you have to pick one of them and make it your standard for operation. So either that bit is going to guarantee that the number of ones in the whole 9 bits is always even. In that case, we call it even parity. Or it's going to guarantee that the number of ones in all the 9 bits is always odd. And in that case, we call it odd parity. So simply, if my message was 0, 1, 0, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8. If it was like this, and I'm using even parity, I'm going to make this one a 0, right? Because in this case, already I have even number of ones. If I add one more, the total is going to be odd. So if I'm using even parity, this is going to be a 0. If I'm using odd parity, then in this particular message, I will add a 1 in the parity bit, and so on for every single block, maintaining either an even all the way or odd all the way. You cannot mix. If you mix, the receiver will lose what's happening, right? When the receiver receives the 9 bits, it just goes across them and check. If our method was even, it has to find that the number of ones is even. If not, this means between the sender and the receiver, something changed the bits, and this means an error has occurred, okay? So anyways, for the keys, for the 64-bit keys, they are not using all of them because for a key to be generated, it's supposed to be that every bit in there is independent by itself. They are not reliant on each other. But they decided that 64 bits, we will use 56 as actual key value, and then we will add a parity so that we can check if someone altered or some error happened in the transmission of the key when I was sending the key to the receiver side or sharing the key across the communicating parties, okay? So this means my key size is actually 56 bits. Now that 56 bits with nowadays computational power can be broken in less than minutes, just using brute force, right? I will keep trying the mixture of all the possible values of the 56 bits until I get some information that makes sense. Either I start receiving an image or a PDF file, or I start receiving a text or an email or whatever, then okay, I know that this is the key, right? So that's why now there are other standards relying on the DES with some modifications. Basically, giving it a larger key with some other modifications. We'll mention it later on. Okay. So how does the DES works? DES is reliant heavily on the Fiestal operation that we mentioned a while ago, right? The one that we were talking about just like 10 minutes or 15 minutes ago, okay? This block that you see here includes all the operations performed in the DES standard, okay? Those blocks, round 1, round 2, up till round 16, are exactly the Fiestal that I mentioned earlier. So they include inside them the block of the Fiestal, upper part, or sorry, right side, left side, and then the operation of substitution using the F function with a subkey to produce the right side of the next, and the left side is produced simply by moving the right side using the permutation operation for each round. And how many rounds we have? 16 rounds. Why 16? I'll mention later. Okay? And for each one of them, we have a separate subkey. The only difference here is we don't show here the decryption. Again, the decryption is going to be reverse operation similar to what we mentioned, and it's bottom up instead of up down, okay? But we show here also the operation of deriving the subkeys, okay? And the subkeys are derived from the original key, which is 64, but we know that only 56 out of that are the key, by using a permutation, a particular permutation that takes every bit in a certain location, moves it to another known location, and then after that permutation, we perform a 1-bit left shift circular. So I have the set of bits, I take the last one, bring it as the first, and shift the bits, right? That's in each one of those, I do 1-bit shift to the left, and it's circular shift. So whatever exits out comes back from the other. You know how to do, you know what's a circular left shift, right? And it's with 1 bit. Effectively, what's gonna happen, by the way, even though it says permutation choice 1, choice 2, choice 3, and so on, but, sorry, permutation choice 1, but here notice it's permutation choice 2, 2, 2, 2. So here, in all of these steps, we are performing the exact same permutation on the different subkey generation steps. The only part where we perform a different permutation in terms of the rearrangement is the starting permutation here. Here, okay? And then in all those steps, we do the same permutation, but it produces a different value. Why? Because of this shift. Every time I take the key, the original key, and I do 1-bit shift, and then I do the permutation, I produce something completely different, right? I shifted 1 bit, and then with the rearrangement, gives me something completely different.
Okay, rearrange.
Yes, so shift, rearrange, and then take this shifted one more time, perform the same rearrangement, you will get something completely different here. Shifted one more, something completely different, and so on, okay? So, supposed to, the way we do the permutation mixed with this known shift is gonna produce keys here, sub-keys that meets the criteria that I mentioned earlier. It's very difficult because all the time permutation operations are very difficult to reverse them, right? And not only that, but the sub-key here is gonna also be somewhat different, as I mentioned, completely different from this one, completely different because of that 1-bit shift that we perform here, okay? Yeah, there is a operation inside here that performs some kind of compression. So you take 56, you do the permutation, but you only pick 48 at that permutation. It doesn't take all the 56. لا, these are sub-keys. في الآخر أنت the actual thing is the 56 that you use here. These are generated from the original one. The reduction here has a particular implementation reason. But anyways, again, you have to keep in mind that inside here, those 48 are supposed to be mixed with 32. Because 64, we take only 1/2 of it and we mix it with the key. So there is another compression operation happening inside here as well. You take the 48, you make them somehow 32 to mix them with a 32 only. Or you mix them with 48 that are the 32 appended with something, and then you take out of that the 32, okay? Rounds, but the only addition to the Fiesta rounds is an initial permutation function, a swap function here that takes the lower, makes it higher, and the higher, or the right makes it left, and the left makes it right, just a swap, that one, and an inverse of that permutation. This is how we define the encryption operation of the DES. What is the permutation function? How does it look like? And inside here, don't forget that we have something called the F, the encryption function, right? Are these somewhere defined? Yes, in your book, if you go to Appendix B of the same chapter, the chapter has 2 appendices. One of them describes in details how the F, the encryption function, looks like. It's representing something called the S-box function, okay? And it has a table that shows you what's going to be the output of the S-box function for every possible input of the 32 bits to it, okay? And it shows you also the permutation. Bit number 3 goes to location number 7, bit number 2 goes, so it shows you all these details of the implementation. It's a standard, so the standard has to be published, right, for people to implement it the right way. However, that standard, the DES, has created actually a conspiracy theory. Why? If you look at the definition of those S boxes, the encryption function, and if you look at the permutations, okay, they are given in tables that shows you what you should do. There is not a single description of why it was given this way. Okay, that's number one. That's one reason for the conspiracy theory. People have been saying when the standardization entity, the NEST, has designed this, they should have released why it's done this way, or what does this way, particularly for the S box, which is supposed to be a logic function, and someone should give it to me as a written function, and then I can perform the mix between the key. No, they are giving it in a table that says for these values of the bits at every location of the key and the plain text, here is what's going to be the first output, the second output, the third output, and so on, okay? So because of that, and because of the usage of, people are not convinced that the reduction from 64 to 56 was actually because they needed to add some parity. Many people said, okay, if they wanted to transmit the key, they could have added the parity after the 64 bits, right? So it's not that much, 8 bits extra, but you keep the 64, which makes it much stronger. So why reduction to 56, okay? And the conspiracy was that the NEST as an entity, as a standardization, which belongs to the government, had in the design some particular hidden weakness that allows them to break the encryption of anyone. Whenever they want to listen to your communication, they can easily break the encryption. And they didn't release the function expression or the intuition, and they didn't say why they reduced, or they came up with an invalid reason for why they reduced from 64 to 56, because this is the way they guaranteed that this weakness is only known by them, but nobody else could figure it out. People driven by this conspiracy theory have performed a lot of analysis on DES. And that's the reason why we have a rich literature in cryptography driven by the conspiracy of the DES. Until today, they couldn't figure out anything. Some people found some irregularities in the behavior of the S box based on the table given, but they couldn't again come up with a clear reason that whether there was some weakness that nobody knows about, where that weakness is, nobody could figure it out until today. But the outcome of the study that was done on the DES encryption enriched the cryptography literature a lot, and it was key for further developments of cryptography, only because people believe that there is something hidden that they need to figure it out. Okay? Anyways, is that conspiracy theory true or not? I don't know. It's in your book. You can find it on the internet, but nobody could say today it's true or just some imagination. We don't know. Okay?
So why they kept the S function or the F function constant? Why it's not something changing? Why it's constant logic that can apply on every single application?
If it is changing, then you need somehow to maintain that change between the encryption and the decryption side, right?
Yes.
When you change the function, then somehow they have to communicate that together as well, right? So we mentioned earlier that the main philosophy of cryptography is all your algorithms and operations are fixed, known to everyone. The only aspect of security is hiding the key. That's it, right? Otherwise, it becomes, from an implementation point of view, it becomes a big issue, right? Yeah, impossible, right? Okay. This example shows you different keys through different rounds, and the output right side and left side, just to show you like numeric values for the encryption process. Doesn't matter that much. It continues until it reaches round 16. Okay. Here in this table, it's very important. It shows you that actually what they call here nowadays computational capability that we see here is like 4 or 5 years old. So this is not nowadays. But with that computational time, 4 or 5 years, computational capabilities 4 or 5 years ago, the DES could be broken using brute force, typically within 1 hour. So 1 hour of trial and error on all possible keys, and at some point you will figure out the key. Okay. Nowadays, I would say in 5 to 10 minutes, depending on the computer that you are using. And I'm not talking about supercomputing. I'm talking about your laptops or even your tablets, because they have much more advanced processors, much faster ones, as opposed to 5, 6 years ago. Okay. This shows you that for the DES, with simply increasing the key size from 56 to 168, this 1 hour number became 10 to the power 29 years. If we say nowadays, you can divide that number by 100, we are 100 times faster than 4 or 5 years ago, then it becomes 10 to the power 27 years to break the key or the encryption using brute force attack only. So you can see how the key size increase makes a big difference in terms of protection against brute force attack. Okay. This was calculated rather than talking about particular clock speed and number of computations. They tried to make the calculation based on an estimated, based on the power and number of computations estimated for 1 round and so on, an estimated time or an estimated, where is that? An estimated speed of performing decryptions per second. So here we are assuming in all of these a 10 to the power 9 decryptions per second. So if I have things coming to me and I assume a particular key and I'm reading the ciphertext, I'm going to apply that to number of messages equal to 10 to the power 9 messages every second. So that's not very slow, but it is doable even with computations that was like 4 or 5 years ago. Nowadays, probably this number is 10 to the power 11. So it's 100 times faster, okay? In addition to DES, the one that we discussed now, the same standardization organization came up, I think it was in the 90s, came up with an enhanced version called triple DES. Typically, they write it 3 DES, okay? And that one is still valid today. As you see, the key size is larger, but not only that, the reason that they call it triple DES because it takes the message, it applies DES to it 1 time with a key, with a main key, and then it generates another main key, applies that to the encrypted one more time, and then generates a 3rd main key, applies the DES operation to it 1/3 time, and the output is your encrypted or cipher message, which is going to be sent to the receiver, and the receiver is going to reverse those 3 times as well, right? So now the protection even is much more complicated, just to also protect against any other attacks such as cryptanalysis or any other types of attacks. Are there any other types of attacks other than cryptanalysis? Yes. Okay. One new, like nowadays era attack, and I'm going to stop at this point, is something called the timing attack. The timing attack until today is kind of a threat, but not an actual attack. Okay? Remember the difference between a threat and an attack. A threat is something that can possibly happen. An attack is something that happened or definitely can happen. Okay? For the timing attack, nobody yet managed to break a full encryption system using the timing attack. What does the timing attack rely on? It relies on the fact that on electronics level, when you do computations including zeros only, right, the calculation is slightly faster than when you do computations that involves a 0 and a 1 or 1 and 1. That depends on the transistor going up and the transistor going down timing. So some behavior at the electronics level of transistors, okay? And accordingly, by monitoring, if I know where is the start and the end of each message, which typically is known, at least I know packets, how big they are when they are transmitted, right? So if I monitor that channel and I see that the generation of a particular packet takes slightly longer, and then the generation of the next one takes slightly shorter, and so on. I can, by doing this operation repeatedly, I can estimate the number of ones in the key used for encryption. Because the larger the number of ones, the more time it will take. But then it's not only that, but there's also the number of ones in the message. So if I have some known plain text, and I know its location in the ciphertext, and I figure out how long it takes, by repeated monitoring, I can get an estimate using timing only operation. I can get an estimate how many ones are there in the key. And I know the size of the key. By knowing that my key must include this number of ones, the search space gets reduced a lot, right? So I exclude anything that does not have the same number of ones, which reduces the size of the keys that I can search through for a brute force attack. And this means less time to break the system. Did anyone manage until now? Because again, that estimate is typically erroneous. It doesn't really, it's not that accurate. And if you try to rely on it, you have to say, okay, plus or minus 2 or 3 more ones. So 3 more ones or 3 less ones. And then the reduction until now with the key sizes that we use nowadays, which are typically 128 or 256 or even 1024 bits, timing attack has never managed to break a system, but it's a threat that exists out there. And DES can be attacked using that method. Similarly, also when we talk about the asymmetric RSA, it can be attacked using that. It can be, but nobody managed yet to break the system using this method, okay? We mentioned already, we talked already about, this slide, sorry. I said I will finish at the last one, but I'll finish at this one. This slide says, why exactly you stop at 16? Using some mathematical analysis, and we are not covering that neither in this course nor in advanced course in encryption. It requires really high speciality in the domain, not even my specialty, okay? You can do mathematical calculations to show that cryptanalysis, when performed on DES, or the Fiestal, basically, the Fiestal rounds, if you stop at round 15, the number of steps, the number of calculation operations that you have to do for cryptanalysis is slightly smaller than brute force. So this means that your system is weaker because it can be attacked by cryptanalysis, okay? And if you do 16 rounds and you try to do cryptanalysis, not brute force, you will find that cryptanalysis takes slightly longer time than brute force, which means that any attacker will do what in that case? Brute force, because they will always seek the, and since by default the protection in our encryption system is upper bounded by the brute force attack, because that's the ultimate attack that can always succeed, but its problem is that it takes a very long time. So it's sufficient to complicate your cryptanalysis so that you reach brute force. Complicating it after that is useless because any attacker is gonna just use brute force. Cryptanalysis is no longer useful, and you are only adding complications and more computations, but the extra protection that you are doing is useless because nobody's gonna use cryptanalysis on that system, okay? So that's why you have to stop at 16. You cannot, you should not, as a clever designer, go for more. Shukran, enough for today.